Inductors are manufactured with either 3% or 5% tolerance because these values represent a good balance between cost and accuracy. Inductors with tighter tolerances are more expensive to manufacture because they require more precise materials and manufacturing processes. Inductors with looser tolerances are less accurate, meaning their inductance may vary more from their specified value. For most applications, inductors with 3% or 5% tolerance are sufficient, as they are relatively inexpensive and provide adequate accuracy. However, for applications where precise inductance is critical, inductors with tighter tolerances may be required. Considering the advantages and disadvantages of inductors with different tolerances, a 3% tolerance offers low cost but less accuracy. A 5% tolerance provides moderate cost and moderately accurate inductance. Meanwhile, a 1% tolerance, although not frequently mentioned in the original query, would offer high cost with very accurate inductance. When choosing an inductor, it is important to consider the cost and accuracy requirements of the application. For most applications, inductors with 3% or 5% tolerance are a good choice. Let's elaborate on the factors influencing the choice of inductor tolerance. Cost is a significant factor. Manufacturing inductors with tighter tolerances demands more sophisticated equipment, skilled labor, and higher quality materials. This translates to increased production costs, which are then reflected in the final price of the inductor. Accuracy is equally crucial. In circuits where precise inductance values are paramount, such as resonant circuits or filters, using inductors with tighter tolerances is essential. This ensures the circuit performs as designed and meets the required specifications. For instance, in a radio frequency or RF filter, even a small deviation in inductance can shift the filter's cutoff frequency, leading to suboptimal performance. Now let's discuss specific applications where different tolerance levels are preferred. In general-purpose applications such as power supplies and non-critical signal conditioning circuits, inductors with 5% tolerance are often adequate. These applications typically don't require extremely precise inductance values, and the cost savings associated with using 5% tolerance inductors can be substantial. On the other hand, in high-precision applications such as medical devices, aerospace equipment, and scientific instruments, inductors with 1% or even tighter tolerances may be necessary. These applications demand the highest level of accuracy and reliability, justifying the higher cost of using tighter tolerance inductors. When selecting an inductor, engineers must carefully consider the trade-offs between cost, accuracy, and performance. There's no one-size-fits-all solution, and the optimal choice depends on the specific requirements of the application. In some cases, it may be possible to compensate for the effects of inductor tolerance by using other circuit components or calibration techniques. However, these methods can add complexity and cost to the design, so it's generally best to start with an inductor that meets the required tolerance specifications. It's also worth noting that inductor tolerance can vary with temperature. As temperature changes, the inductance of an inductor may also change slightly. This effect is known as the temperature coefficient of inductance, and it can be an important consideration in applications where the inductor will be operating over a wide temperature range. In such cases, it's important to choose an inductor with a low temperature coefficient of inductance to minimize the effects of temperature variations on circuit performance. Furthermore, the manufacturing process itself influences the final tolerance achieved. Inductors are often made by winding a wire around a core material. The precision of the winding process, the uniformity of the core material, and the stability of the wire insulation all contribute to the overall tolerance of the inductor. Manufacturers employ various techniques to control these factors and achieve the desired tolerance levels. These techniques may include automated winding machines, precise material control, and rigorous testing procedures. In addition to tolerance, other important parameters to consider when selecting an inductor include inductance value, current rating, saturation current, and self-resonant frequency. Inductance value is the primary characteristic of an inductor, determining its ability to store energy in a magnetic field. Current rating specifies the maximum current the inductor can handle without overheating or damage. Saturation current is the current level at which the inductor's inductance begins to decrease significantly due to core saturation. Self-resonant frequency is the frequency at which the inductor's parasitic capacitance resonates with its inductance, causing the inductor to behave like a resistor. When choosing an inductor, it's important to select one that meets all of these requirements for the specific application. In summary, the choice of inductor tolerance depends on a complex interplay of factors, including cost, accuracy, and performance. Inductors with 3% and 5% tolerances offer a good balance for many applications, while tighter tolerances are necessary for high-precision applications. Engineers must carefully consider all of these factors when selecting an inductor to ensure that it meets the requirements of the application. Now let us discuss more about the accuracy. An inductor's accuracy is directly related to its tolerance. Tolerance, expressed as a percentage, indicates the allowable deviation of the actual inductance value from the nominal or specified value. For instance, an inductor with a nominal inductance of 100 microhenries and a tolerance of 5% can have an actual inductance value ranging from 95 microhenries to 105 microhenries. In applications where precise inductance is crucial, such as in resonant circuits, filters, and oscillators, even small deviations from the nominal value can significantly impact circuit performance. For example, in a resonant circuit, the resonant frequency is inversely proportional to the square root of the inductance. Therefore, a change in inductance due to tolerance will directly affect the resonant frequency. This can lead to detuning of the circuit and reduce performance. Similarly, in filters, the cutoff frequency and attenuation characteristics are dependent on the inductance values. An inaccurate inductance value can shift the cutoff frequency or degrade the filter's ability to attenuate unwanted signals. In these types of applications, it is essential to use inductors with tighter tolerances to minimize the impact of inductance variations on circuit performance. In contrast, in less critical applications such as power supplies, decoupling circuits, and non-critical signal conditioning, laser tolerance inductors may be acceptable. In these applications, the exact inductance value is not as critical, and the cost savings associated with using laser tolerance inductors can be significant. It's important to note that the tolerance of an inductor can also be affected by environmental factors such as temperature, humidity, and aging. Temperature variations can cause the inductance value to drift due to changes in the physical properties of the core material and winding. Humidity can affect the insulation resistance of the winding, leading to increased losses and changes in inductance. Aging can cause gradual changes in the core material and winding, resulting in long-term drift in inductance. To mitigate the effects of these environmental factors, manufacturers often specify the tolerance of inductors over a certain temperature range and under certain humidity conditions. They may also use special materials and manufacturing processes to improve the long-term stability of the inductors. When selecting an inductor, it is important to consider not only the initial tolerance but also the expected environmental conditions and the required long-term stability. In some cases, it may be necessary to use inductors with tighter tolerances or to implement compensation techniques to minimize the effects of environmental variations. Now we can discuss cost implications. The cost of an inductor is significantly influenced by its tolerance. Inductors with tighter tolerances are generally more expensive to manufacture due to the need for more precise materials, manufacturing processes, and testing procedures. The materials used in high-precision inductors often have tighter specifications for permeability, temperature coefficient, and other characteristics. The manufacturing processes must be more tightly controlled to ensure consistent winding, core alignment, and lead termination. The testing procedures are more rigorous, requiring more sophisticated equipment and skilled personnel to verify that the inductors meet the specified tolerance. In contrast, inductors with laser tolerances can be manufactured using less expensive materials and processes. The winding can be less precise, the core alignment can be less critical, and the testing procedures can be simplified. This results in lower manufacturing costs, which are reflected in the lower price of the inductors. The cost difference between inductors with different tolerances can be significant, especially for large quantities. For example, a 100 microhenry inductor with a 1% tolerance may cost several times more than a similar inductor with a 5% tolerance. This cost difference can be a major consideration in cost-sensitive applications, where the overall cost of the product is a critical factor. In these applications, engineers must carefully weigh the cost savings of using loser tolerance inductors against the potential performance degradation. In some cases, it may be possible to compensate for the effects of loser tolerance inductors by using other circuit components or calibration techniques. However, these methods can add complexity and cost to the design, so it's generally best to start with an inductor that meets the required tolerance specifications if the budget allows. Furthermore, the cost of inductors can also be affected by factors such as size, shape, and packaging. Smaller inductors are generally more expensive than larger inductors due to the challenges of manufacturing them with the same performance characteristics. Surface mount inductors are generally more expensive than through-hole inductors due to the additional manufacturing steps required to attach them to the printed circuit board. When selecting an inductor, it is important to consider not only the tolerance but also the other factors that affect cost. A careful analysis of the application requirements and the available inductor options can help engineers to choose the most cost-effective solution.